Dear participant, good evening to all. I welcome you all for the session 8 of the AST sponsored ATAL faculty development program on redefining innovation, AI and ML for Industry 5.0. This session we have with us Karthiga, who will be handling the session on Healthcare 5.0, AI and ML in personalized and predictive medicine. We are happy to welcome Karthiga among us for this session. Karthiga at present is working as a senior machine learning engineer at Intelliswift and LTTS company for the past 2 years. Then before that, she was working at machine learning and computer vision engineer at Google for 1 year. Then she had experience at the computer vision software engineer at Hancock in California, United States. Then as an artificial intelligence engineer at Unique Inc. Done internship there. Then she worked at CSIR as a graduate apprentice for 1 year. She did a Bachelor of Engineering in Electrical Engineering at CIT. Then completed her master's in Electrical Engineering at North California State University, USA. She has completed many certification courses, and has done various projects like detecting stages of leaf wilting in soybean plant, phase classification using Viola-Jones algorithm and ensemble learning, and many more classification and image processing and AI projects. We are very pleased and happy to invite her for this session. Welcome, Karthiga. On behalf of GC Salem, we invite you for this session. Thank you. Yeah. Yeah, I unmute you.
Hi, everyone. Thank you so much for that introduction, sir. And I'm really happy to be able to handle this session in Healthcare 5.0 today. A little bit more about the work that I'm currently doing. One of my clients is Almeida Health Insurance, right? So they're a health insurance company, and what they do is they collect a lot of forms from different hospitals, and then there is a separate process of digitizing those forms and using LLM, computer vision, optical character recognition models to be able to perform some kind of analysis on them, and to also formalize these health records into one common database. And today I have created my slide deck in such a way that I show some examples, I show some videos, and also talk a little bit more about my work. And I really hope that you all find it engaging and interesting. So without further ado, I'll jump right into it. Trying to share my screen. Sir, I'm not able to share my screen.
One second.
Sure.
Yeah. Can you please try now?
Yes. Yes. Can you all see my screen?
Yeah. It's fine now. Yeah, please.
Yes. All right. So as I just gave a brief earlier, today we're going to explore Healthcare 5.0, which is AI and ML in personalized and predictive medicine. I'm sure that a lot of you might have already seen some samples of AI and ML in predictive medicine. I'm pretty sure that a lot of students choose such projects for their final year thesis and final year projects. So the difference, the evolution that we're moving into is in personalized medicine. And to be able to explain this further, let's go and explore what the evolution of healthcare has been from Healthcare 1 to Healthcare 5, which is the stage that we're going to be progressing into right now. So Healthcare One is nothing but village medicine. So basically, when somebody is sick, you go to your physician, and they could be a Siddha doctor, they could be somebody that you trust a lot in your family, and they would prescribe some kind of medications to the best of their knowledge, right? And say, for example, if I have a common cold, right, and I live in Tamil Nadu, probably my mother or my grandmother might make a pot of rasam for me, right? But let's assume I was a British citizen, right? And if I had a common cold, my mother or my grandmother would have made me a pot of stew, right? So that's Healthcare 1.0. So Healthcare 1.0 is like completely dependent on the physician, their knowledge, and their accessibility. The knowledge from Healthcare 1.0 was not very transferable. Say if the physician that you go to on a daily basis does not live there anymore, then probably that knowledge cannot be transferable. Another example that all of us might have dealt with when we were younger is when we fall down and we used to get hurt, right? Our parents, they just give us maybe like talcum powder or coconut oil, and then they'll say, oh, that's going to heal it. That was never going to heal the wound anyway. But yeah, that's what Healthcare 1.0 was. Now, Healthcare 2.0 is what modern allopathy really is, right? So the discovery of penicillin, which is like the antibiotic, it was a cure to so many diseases which was once considered fatal, and which really affected lives, right? So plague, polio drops, etc. Not only that, standardized diagnostic instruments like X-rays, vaccines, and standardized techniques that are monitored by, say, the World Health Organization or the Indian Medical Association. So all of this comes under Healthcare 2.0. This is what the doctors go to their colleges to study for. Healthcare 3.0 is digitization, right? I would like to argue that Healthcare 3.0 is not as advanced in India as it should be. However, in other continents like Europe or America, it's still a bit more advanced. Healthcare 3.0 is nothing but digitizing your information, right? So over here, we have something called as an EHR, which is an electronic health record, right? So say, for example, right now I'm living in Pittsburg, Pennsylvania, and I'm suddenly changing my job, I'm changing my city, and I'm going to San Francisco. So my primary care physician is someone that I am not used to, and the hospital that I'm visiting is not the same brand. Say, for example, if I'm visiting Apollo right now, I might go to Fortis later, right? But here in the US, they have a way of digitizing your health record so that no matter where you move to, your medical history is something that any doctor can see. And it's always going to stay with you whether or not you carry it around in a physical file. This Healthcare 3.0, I would argue, is the main reason as to why we are seeing this progress toward Healthcare 4.0 and 5.0, which is an extremely ambitious evolution that we're going to move towards. Healthcare 4.0 is nothing but connected health, right? So we see a lot of people these days with their Fitbits, their smartwatches, their Apple Watches, right? And by having these kind of sensors on their hand, they are able to continuously monitor their sleep quality. They're able to continuously monitor their activity levels, their cardiovascular activity, menstruation tracking apps around, and your basal metabolic rate. These are all things that are now a bit more accessible in either your smartphone or your smartwatches, and everybody is able to stay connected. Not only that, apps like Practo is something that I have to bring in here because, say, in India, telemedicine is now enabled through apps like Practo. So if I were to live in a very remote village without, say, a specialist, like, say, for example, I'm having a foot pain, right? And I want to visit a podiatrist, but I don't have a podiatrist in, say, Dindivanam, which is where I'm from, right? Then I can go on to Practo and I can have access to a doctor in Mumbai who would be able to still virtually consult with me and help me with my healthcare needs. So this is Healthcare 4.0. And the main reason why we were able to have Healthcare 4.0 is the IoT, burst, and also the accessibility to internet and, cheaper data storage and things like that. Now, Healthcare 5.0 is the next stage of evolution that we are aiming to go into. Now, Healthcare 5.0 is using AI, robotics, machine learning, technology, all of these features to be able to aid and assist doctors in the kind of diagnosis that they perform, right? So in the upcoming slides, we'll delve deeper into what we can expect in Healthcare 5.0. So what will healthcare look like in the next decade, right? So the three key words that we're going to focus on is it's going to be personalized, it's going to be data-driven, and it's going to be predictive, right? We always keep saying this very ancient proverb, prevention is better than cure. But ironically, in the field of medicine, that was never the case. We always go to the doctor only after we fall sick, right? However, with Healthcare 5.0 on the way, we should be able to prevent a disease before it can ever happen, right? So why now? Why is Healthcare 5.0 happening now? And why did it not happen in all these many years, right? So neural networks. We all think that neural networks, LLMs, or computer vision, right? These are very new algorithms, and this is the latest bubble in tech and AI. But I'd like to tell you you're wrong. So neural networks have existed since 1940s, right? But the one thing that did not exist in the 1940s was electricity, widespread access to electricity, basically, GPUs, right? Storage. We all now have, 64 gigabyte storage very easily in our smartphones, right? But we all remember of a time when, having an 8 gigabyte storage on a smartphone was considered a very good, amount of things to store, right? And also a scalable infrastructure, basically cloud storage. So right now, whether or not I have a GPU hardware in my laptop, or whether or not I have GPU in my a localized GPU in my university or college that I'm studying, I can simply have access to cloud services like Azure or AWS or GCP, or even a simple Colab environment, which is there in everybody's Google Drive, right? Even if you're not that proficient in cloud technology, everybody has access to GPUs, right? And it's because of this widespread access that right now it is possible to have this, Healthcare 5.0 evolution. Not only that, as people in academia, we all know how important it is to have funding to be able to enable any kind of research breakthrough to happen. Earlier this year, it was very popular news that, our president of America, Donald Trump, was funding almost $500 billion to be assigned towards Stargate, right? And Sam Altman was one of the forefront leaders of having this enabled, right? So OpenAI is one of the most popular companies in the space of LLM and, Stargate. He was the talk of the town at that time. But that particular funding and that particular project, which was basically funding towards data centers, right? A large data centers that can help AI scale to so many people's homes, right? It was also in benefit of companies like the Google DeepMind, Tempest, Path AI, and several other companies, right? So AI infrastructure, so many data centers and geological centers for data centers are all also a contributing factor. Right. And we also know the industry leader right now, household name almost is NVIDIA, right? And NVIDIA comes up with GPUs that can range anywhere between like small chips that are meant to fit on a computer, even smaller chips that are meant to fit on, augmented reality glasses or watches, to all the way up to supercomputers, right? And so these kind of infrastructures that are there to enable and facilitate AI development of all scales and sizes, from very small models with maybe even 500,000 parameters to right now we hear about Llama and other models of 3.5 billion parameters, right? And Google TPUs AWS Trainiums. These are all some of the hardwares that I'd like to mention over here. Another thing would be internet access, 4G, 5G. This is way much more widespread these days. Everybody has them, and that's also a contributing factor. Not only that, skills and ecosystem. So literacy, computer literacy is way much more common these days than what it once used to be, right? So that's something that helps bring in more talent to be able to implement this AI and make it much more widespread, right? So yeah, so these are all the reasons. Right now, we're in the right time and the right place for this evolution to happen. This could have happened anytime in the past, but all the factors did not ever come together. But right now, since all of that is coming together, we're going to see this next stage of evolution happening, right? Next, I'm pretty sure that all week this week, we would have seen much more about the AI ML deep learning fundamentals. So I'd still like to talk about these basics in a way that I intuitively understand. So I've also having a demonstrative notebook. Before that, let me go through the definitions once, right? So we have AI, ML, and deep learning. So what's the big difference, right? Artificial intelligence is nothing but this huge umbrella which has so many things that it may include. It can be anywhere from a big robot to a small computer program. Everything is incorporated under this big umbrella of artificial intelligence. Basically, allowing a computer to make decisions itself is an anything that can do that is considered as an AI, right? Machine learning is a small subset of artificial intelligence where there are so many algorithms, right? To name a few, support vector machines, random forests, decision trees. So all these algorithms use so many different methods, right? Some of them might split it into different trees. Some of them might want to see like a trend based on a graph. And some of them, like clustering algorithms, right, are trying to group different data points together. And by using so many different methods and techniques, right, for different use cases, some algorithms might be more useful over the other. Now, deep learning. Now, what's the difference between why would we use deep learning and when would we use machine learning? So for machine learning, one of the prerequisites is that the data should be structured. So this could be maybe tabular data. So we always see machine learning examples, right? We see stock market prediction, right? Why are we able to see that? Because we have so many companies, we have so many dates, and we have like data points to exactly predict which date, which value is increasing, decreasing, etc. And what is the stock market values that we have? They're numbers, right? Dates are numbers, and what the increasing value, which is some money value, monetary value, it's a number. So you're able to make predictions using machine learning. But now let's assume a big textbook of information, right? I want to be able to teach, geography, and I have this big textbook of information. How am I going to teach the computer to understand these geographical terms? How am I going to teach a computer? So will I first program the computer with all sorts of English grammatical rules and then later feed in this information? But even if I can do that, we all know how complicated a language like English is, right? Where there are so many rules, and in different contexts, the rules can change. In different tenses, the rules can change, right? And now imagine now scaling this across so many languages in the world. There's going to be Arabic, there's going to be Tamil, there's going to be Telugu, there's going to be so many languages. How are you going to allow a machine to learn all of this? So when we look at unstructured data, that's when neural networks come in, right? So one thing that I generally don't like when people talk about deep learning is that, they just say it's a black box and then finish the topic right there. So if it's a black box, where is my motivation to learn what goes under the hood, right? So right now, I'm going to show you a notebook which is still not going to capture the entire soul of deep learning, but I hope that it will help you understand the intuition behind deep learning, right? So let me open the notebook. Yes. Are you all able to see the notebook? Can someone?
Yes, visible. Yeah.
Yes. So here in this notebook, what I've tried to do is I'm going to try to show some sample data, right? And I'm going to try to use different kind of classifiers, from simple classifiers to deep learning based classifiers, and show like how and why something works and why something doesn't work. Over here, I'm just importing some basic libraries. Here is a helper function, which is going to generate some data samples. Over here, I've just generated 200 data samples, which are non-linearly separable. So non-linearly separable is just basically that I cannot just say like, okay, upper half is data sample X and lower half is data sample Y. Here, I'm denoting with the colors blue and red for two different classes, right? So in the first case, what I'm going to do is I'm going to try to fit a linear classifier. Now, what is a linear classifier, right? It's as simple as the polynomial equation y is equal to x plus b, where y is your label. So basically, y is I'm trying to predict blue, or I'm trying to predict red, right? In this case, I'm trying to predict that perfect line which separates blue from red. So this is what I'm trying to do. So here I'm using the machine learning model support vector kernels, right? And I'm trying to do the linear separation. As you can see over here, our data points are radially separated, which is basically all the blue points are in the center and all the red points are somewhere in the outside of the center, right? I'm trying to now draw a line to separate these blue points. It's very hard to draw a line and separate points when there is a clear center and then there is a clear separation. However, my linear classifier does its best. What it does is it's trying to push most of the blue points away to the right side of the table, and most of my red points are here to the left side of this table, right? So it's definitely not a good model, but I understand why it's performing this way. So y is equal to x plus b, I'm getting a straight line separating the two models, right? Two data points. As you can see over here, the accuracy is pretty low. It's only about 0.59%, which is slightly better than a random guess. Now let's go to a polynomial classifier. Now, what would be a polynomial classifier? So we all know about the quadratic charts, right? Like if we think about it, y is equal to x plus b. How do we usually draw it in algebra? We just draw a straight line going right through the axis. Now, when we go to y is equal to x square, we draw a parabola, right? And then y is equal to x cube. We draw almost like the tan H kind of chart, right? So here, what I'm doing is I'm doing a polynomial classifier of, its own degree. So here I've chosen the number 5, right? It's a random number. So this is called a hyperparameter. Basically, a hyperparameter is a number where there is no right or wrong number to put. It's a trial and error method, right? If I'm unsatisfied with the results from this number, I can either increase or decrease. And that's the main job of an ML engineer, to develop the intuition as to when to increase, when to decrease, when is the model overfitting, when is it underfitting, etc., etc. But the main point over here is we can see that this particular polynomial classifier, which has basically the higher powers, instead of just x plus b, I have x squared, x cubed, right? Here in this case, it would be x to the power 5, right? X to the power 5 plus a bias variable. It's able to give me a proper circular separation. We're able to see that the blue is contained in the inner rims and the red is contained in the outer rims, right? And here, even the classifier accuracy, you can see the jump. It has gone to 0.95. Whereas using just a linear classifier, we got only a 0.59% accuracy, right? Exactly like the alternate. Here is another case of a polynomial classifier that is able to give a more complex boundary, right? Over here, we just had a sphere. Here we're having a more complex boundary. So you can adjust the degrees as in how you want to make these boundaries be different according to your data set and sample, right? So over here, I'm guessing that the model has not tried to separate blue from red. Rather, it has tried to separate like the data points from where the data points are not there. So yeah, must look into that as to why that's happening. here is just, as we just discussed a while ago, the graphs, right? We see that y is equal to x plus b is this blue line, right? It's going to give you a straight line going right through the axis, right? Y is equal to x square is going to give you this orange line, which is a parabola, right? And y is equal to x square plus 3, or basically any bias terminal, will just give you a little bias. It's going to raise you up from this axis, right? And then this red term, which is y is equal to x cube, is giving you this kind of curve. Now, why are we talking about degree of freedom over here? Because as we just saw, like if we have to draw a line separating these data points, right? The more degree of freedom that we have, the more curvy your line can go and make that boundary and separate these data points from each other. Over here, I have only 2 classes, and this is only a 2-dimensional map, right? Later, we might have multiple dimensions. We might have multiple what can I say, data points. And in those cases, it would help a lot to be able to utilize this multinomial, degree features, right? Now, another heart and soul for the deep learning algorithm is this activation function, right? So what is the deep learning algorithm? This green parabola that we see here, right? Y is equal to x square plus 3. Now, you attach a sigmoid in front of it, and that becomes your deep learning function. Why do we need this sigmoid, right? Because a deep learning function, as much as we say it is a black box, just under the hood, right? Just like how we'll have any kind of bubble sort, Dijkstra algorithm, or any kind of like sorting algorithm, there is one key heart behind this deep learning, and that is the gradient optimization. Now, what this gradient optimization does, in the most simplest of terms, is that if I'm having a data point, I'm passing it through the neural network, and I'm having an output. And what I'll do is I will compare this output. So why we say we need labeled samples, right? For deep learning, it is a kind of supervised learning algorithm. Say, for example, I'm trying to detect cat versus dog, right? I need to have images of a cat. I need to have images of a dog. I also need to have, a label column which says that a cat image is a cat, a dog image is a dog. Okay. Now let's assume that I have a cat image. I have passed it through my neural network, but my model has predicted it as a dog, right? Now I'll have a value, the probability of prediction that it is a dog. Whereas what is the original this thing? It is a cat, right? Now I'll compute the loss. My job now is to minimize this loss. I need to make sure that I do not have such a high confidence of predicting the opposite class, and I try to predict that it is a cat. So what I do is I do this back propagation through an algorithm which is called the gradient optimization algorithm. Now, imagine doing this back propagation on any of these existing formulas. Y is equal to x, y is equal to x square, y is equal to x square plus 3, right? Now, my job is I have to learn, right? And I have to adjust these biases and coefficients. So all that we're doing in a deep learning algorithm is, say, for example, y is equal to x is making one prediction, but y is equal to 2x is giving me a higher accuracy. I'm trying to fix that. That 2x, that 2 is the weight, and y is equal to 2x plus 5. That 5 is the bias. So this is the weight and the bias are what we call as the parameters of the deep learning model. And what we're trying to do with the deep learning algorithm is to predict these exact parameters, right? So now we have a loss function that tells that, hey, your probability was wrong, and you need to go and correct whatever weight and biases you had. How am I going to do this correction? How am I going to correct my W value and my B value, right? I need a differentiable function. Without a ReLU, what would happen if I take a differential for y is equal to x? I just get the answer 1, right? If I do y is equal to x square, if I take a partial derivative, what would I get? I'll get 2, right? Which is nothing but a constant. And if I have only constants and I take away the x factor, if I take away the learnable parameter, x is nothing but the data point, right? If I take away what I have to learn, then what will my model know? My model will be nothing but a combination of constants, and it will be a big sum value at the end. So in order to prevent that from happening, we have the ReLU function, right? So this is a ReLU function. So basically, it's as simple as anything that has a greater value than 0, as long as it's not negative, allow the weights to pass through. Whatever weights are below negative, cancel them out so that they do not have an impact on the final model, right? And I mean, I'm not going to go into the exact details of how the partial derivative, etc., works. I just wanted to give an overall intuition as to how and why that's happening, right? Over here, I'm showing you just an example, degree 40 polynomial, how much it separates. You can see that all the blues are contained within this boundary, right? But it's trying to overfit to the blues. It's trying to not miss even a single blue, whereas it's having a lot of reds. This is the case of overfitting, because you're not supposed to have so many misclassifications either, right? You need to understand what is an outlier, what is not. An example now that we saw in the 2D maps, why do we need deep learning to do this? Why not, existing algorithms, right? This is a 3D representation of the blue and red points that we saw earlier. Now we see how important it is to have these polynomial lines, because it has to go through all these, directions and then do the separation. Right now, it's not anymore just separating into two halves or separating circle and bigger circle. It has to go through the third dimension and separate. But why deep learning still, right? Now imagine there'll be multiple dimensions, which we cannot comprehend. Now, because 3D, I have the ability to draw it on Matplotlib, I'm able to draw it. But what if I have more than that many dimensions, right? How will I be able to depict that? How will I be able to comprehend that? How will I be able to learn from that? Now, this is why we call this a black box algorithm. So I'll show example of an unstructured data set as well. So, okay, first let's go into this example. So I'm just using a deep learning model over here, a custom model I've just built using just 3 layers, one main layer, two hidden layers, and one output layer. In the last, I'm just predicting 0 or 1, right? Red or blue, right? We can see over here by using a very simple deep learning model, the decision boundary is way much more better. It's giving us a much better classification boundary, right? So now when I say multiple dimensions, what could those multiple dimensions be, right? So over here, I have done nothing but taken 4 or 5 English sentences, and I've tried to pass them through an embedding vector over here, a universal sentence encoder. This is the embedding model that I'm using. I'm just trying to represent it in numbers, because a computer cannot understand words at all. So we have the vector representation of words. Now, as you can see, for this particular universal sentence encoder, each sentence has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vector representations, right? And now imagine this going for every sentence in the English language, so many different contexts in a book, and so much data sources, right? And this is an example of multidimensional unstructured data with a numerical interpretation, which we cannot comprehend, with the kind of visibility that we have. Why we need to have a deep learning model, right? I have shown another example of an unstructured data, which is an image, right? So for us, we are able to clearly see that this is a man, and the man is looking through a telescope, right? But what would a computer see? It will see nothing but boxes of pixels, 190, 190, 191, 120, 120, 121, 3 channels. In this case, it is only a grayscale, but generally a 3 GB means it would have been 3 channels of just numbers. But what will a computer interpret from anything from that particular image? So in the CNN concept, we have filters that go through the image and that make these, detection of edges, colors, textures, so many things. So we have so many different filters to do so many different things. Here I have used just 2 filters, vertical filter and horizontal filter. But why do we need a CNN, right? Here I was able to code a vertical filter and horizontal filter. I can just code a filter for texture, color, etc., and I could even code it normally, right? Why do I need to have a CNN and this much computing power and this much expensive algorithm to do this? Because there is no way that I can predict what kind of data input it will be. In this case, it was a real-time image. It could be a 3-scale image. It could be my phone image, right, which is a different format from a DSLR image, right? Or it could be a different, the what do you call it, the landscape versus portrait. It could be different mode, which my computer is not used to seeing, right? It could be a medical image, right, for which I do not know what filters are important. So these filters, what to use also, by the process of backpropagation, a CNN would learn. So yeah, so this is the basics between like AI, ML, and how it progresses to deep learning, and why we need to apply deep learning for some cases. So yeah, I really hope that that was helpful in getting the intuition of these three different paradigms, right? And then obviously we have the supervised, unsupervised reinforcement learning as well. Supervised learning is what we saw right now with the, the cat dog classifier, that example that I said. We'll go into one more notebook explaining this as well. Unsupervised learning is basically like clustering that we have. These examples that we saw, which is nothing but making the blue and red separate, right? Making it into a sphere. This is unstructured. I have not given label. I have not told that this point is a blue point and this point is a red point, but it's able to go and find that decision boundary. So that is our unsupervised learning. And reinforcement learning is predominantly used in robotics. Yeah. So predictive medicine with AI, right? So I'm right here, I'm going to demonstrate 2 or 3 samples as to how predictive medicine has been used in AI so far, right? So this was stage 1. Predictive and personalized medicine is what we're going to be looking today. This is basically like the first portion of today's talk. So we have sepsis early warning, right? So sepsis is nothing but blood poisoning, right? And it's a silent and fast killer. So there was an AI system called the TRUES, okay, and TREWS. So that gave early warnings. So whenever this TRUES system gave warning, if the doctors responded within 3 hours of a TRUES alert, then a life was saved, right? So the mortality rate from sepsis alone dropped by 19%, which means so many lives that would have otherwise died were saved just because of a predictive warning by an AI system, right? Another example is acute kidney injury prediction, right? So DeepMind, which is basically Google's custom house for the deep learning models, etc., right, had made a model for acute kidney injury. And what it does is it would be able to do the prediction 48 hours in advance that, hey, your kidneys are going to fail and you need to act on it right now, right? Then atrial fibrillation detection with Apple Watch, right? So the Apple Watches we know are capable of detecting our steps, our heart rate, our sleep quality, etc., right? So in a large-scale study of almost 400,000 participants, right, AI detected some irregular pulses and sent alerts. And 84% of the time, these people did have some kind of atrial fibrillation, and they reached the hospital on time, because of which they were able to avoid complications. So these are some real life current examples of how this AI has been in use and how predictive medicine has helped enhance quality of human life. So now, why does ML matter in medicine, right? Now we have massive data scale, right? And with massive scale, there's so many different things that humans cannot, identify the pattern. Say, for example, if I, as a student, made a model to predict COVID-19 in 2019, but then there was a different variant in 2023 with a completely different set of symptoms, with completely different set of, effects on the people, then I, as a doctor, might not be able to tell it immediately. But using ML algorithms, I can slowly keep tracking the changes and etc. Right? And so also we are moving more towards a reactive care. So before anything happens, you're 40, your mother had sugar, so you are most likely to have sugar. So try to focus on your health right now. These are things that we see in a lot of our family environments as well. So this is something that's very important, because of which this shift is happening as well, right? Now I'm going to show another algorithm, basically explaining, okay, I might have it somewhere here. All right. So this is going to explain predictive model for ML in healthcare for diabetes, right? So I have used a data set like it's from OpenML. So it was just an open source data set that I found, which had some diabetes information. So it had these fields, which is basically pregnancy, I believe, basal metabolic rate, glucose, blood pressure, insulin, skin thickness, things like that. And apparently, the most important field was this, which is diabetes pedigree function, right? And the age of a person. And it was a label data set, which I found online, which is basically telling a person of these kind of metrics, do they have diabetes? Do they not have diabetes? Here's what I've done. What I've done is I've split it into training and testing samples. So not a lot of data. I only have like 600 samples in the training set and about 150 samples in the testing set so that I can do my validation, right? Here, I'm doing my exploratory data analysis. The first graph I'd like you to remember, which is basically, it tells the number of samples that are not diabetic, number of samples that are diabetic. And this is very, very common case in healthcare systems, right? So in a room of people, everybody will not be sick. Most people will be healthy, right? So when you're collecting data, it's very easy to get, an imbalanced set of data samples where there are so many people that are healthy. So this is important to know as to why we cannot use accuracy as a metric later on. So, sir, Mani sir, how much time do I have left? I wasn't tracking.
Karthika, you have 30 minutes.
Okay, fine.
Okay.
So, all right. Thank you. Yeah. So over here we have logistic regression and random forest models. So that's what I've used over here. So here, two models, right? Logistic regression and random forest. So why earlier accuracy was wrong, right? Say, for example, I'm doing a spam, no spam classification, right? I have 100 emails, of which almost 90% of emails, 99% of emails are correct emails. 1% I'm getting spam emails. I'm putting this into a spam, no spam classifier. Now let's assume that my ML model is predicting with 99% accuracy, 100% accuracy, that all emails are spam. What will be my defect rate? It will be only 1% only I'm getting wrong. But that 1% is what I have to predict, right? So this is why accuracy as a metric is misleading. So I've shown this example to show how to use these metrics, right? Over here, I'm showing the ROC curve and the precision recall curve. So this is the ROC curve. Okay, it's a way to understand how your classifier separates in different thresholds, right? So a machine learning threshold we have. So at 0.2 threshold, 0.2%, if it's correct, then this 0.4%, 0.6%. So I set different thresholds and I do this training, right? So we can see over here that the graph goes like this. The more my graph is leaning towards the top left, the better my model is. Over here, we can see that the area under the curve is 0.82%. Now, if my graph was more leaning towards this diagonal, then my model is nothing but a random guesser. That is a bad prediction rate, right? Similarly, over here, we have the precision recall curve. Precision recall curve is going from top to bottom. This is supposed to be little less. So what we are predicting is, over here, the ROC curve is predicting nothing but the sensitivity. And the sensitivity is give me a second, please. And sensitivity is nothing but catching people. Like, say, for example, if somebody is sick, somebody is healthy, I might as well consider that the healthy person is also sick, so that I do not miss out on classifying somebody who's healthy, who's sick, right? So it's okay that I test 20 people, whereas only 5 people were found sick, right? But I need to make sure that those 5 people who are sick are definitely captured by my ML algorithm. If that was my metric, this is the curve that I'd be looking for, okay? But let's assume diagnosing someone is a bit more harder, right? So like, say, for example, if I want to be tested for, breast cancer, then I need to have a mammography done on me, right? In which case, I would go for the precision recall curve, which is basically, even if I'm sick, I will let you go, but I would, unless I'm specific and I'm very sure that you might have breast cancer, I will not do that procedure on you to make that diagnosis. So if that is more important, then we look at the precision recall curve, right? So I'm going to kind of skip through some slides because we don't have as much time. So so as I said, sensitivity, specificity, and precision recall. These are the metrics that we should look into, other than just accuracy while making these classification, right? So sensitivity is nothing but, did we catch everybody who was sick? Specificity is, did we avoid giving panic to people who are healthy, right? Say, for example, if I'm having an Apple Watch and it keeps telling, oh, your fibrillation rate is low, and stuff like that, then just for using a device, I'll just be in constant panic, right? And it's not a trusted medical healthcare professional to give me that diagnosis. So I need to make sure that my Apple Healthcare Watch has high specificity and not as much sensitivity. So these are some of the things. What device are you designing for, and what use case are you solving for, that we have to look into to do these evaluations, right? So predictive medicine, from scores to action. So is it important to just have good score, good precision recall value, good this? No, we need to make sure that the insights we derive from these models are also actionable insights, right? So what are the failures that can happen, right? Label leakage, right? What happens is sometimes accidentally we'll give the answers. Say, for example, I was recently trying to train a healthcare small language model, right? And what I did was, while teaching the model, I also gave the doctor's notes, and I got really good accuracy. But then I realized that I didn't clean my data properly, and my model is making these predictions from the doctor's notes that are there at the bottom, right? So this is a classic example of label leakage. Data set shift, right? So a model that was trained on COVID-19 data in 2020 will not be able to detect and make the correct prediction on the mutation that happened in 2025, right? In 2020, someone might have died from COVID, but 2025, we rarely ever see cases of fatality from COVID. So that's an example as well. Alert fatigue, right? What would happen if we keep getting notifications on our phones, right? For so many things that didn't deserve our attention in the first place. We will start ignoring some of those notifications, and we will not pay attention to, random notifications. So sometimes if, unless or until something is serious, if the healthcare system is giving an alert in a preventive way, like, oh, just check them just in case, then the doctors will not take that healthcare system seriously. So that's another thing, right? And poor external validation. So in the sepsis model that we spoke of earlier, I'll come back to that particular tale a little later. But basically what happens is, it was trained on synthetic data, and the demos worked really well. And it was basically IBM Watson that prepared that particular sepsis detection model, and they were able to sell it to a lot of hospitals, and a lot of hospitals that assigned long-term contracts and long-term deals. But later, when they were using it on the patients, actually, then they realized that the sepsis model is not making the predictions as intended, because the model was never trained on real-time data. It was trained on synthetic data, and also the patient, symptoms, the patient effects, and everything varied from demographic to demographic, race to race. So many biases happen. So things like that, how we choose our data sources, all count in predictive medicine, right? Now, the core of Healthcare 5.0, as said earlier, it's basically personalization, prediction, and participation. So we've already been able to use ML for predicting, you have like a risk of cancer, you have a risk of this. But personalization is, say, for example, hey, you already have a tendency to have a high blood pressure, but if I give you this particular drug to treat, say, your heart condition, right, then it will impact your blood pressure very severely. Or if you already have sugar, so if I give you this, it's going to impact your sugar. So I'll give you this drug instead, okay? Or, antidepressant drugs, which are much more harder to generalize, because everyone's mental health condition is going to be different. Everyone's preferences on how they want to be when they are, feeling that they need some emotional support is going to be different. So that personalization. And prevention is basically like, prevention is better than cure. So we are not going to wait for a disease to affect us to go and solve it. We're going to solve the disease before it even, manifests itself, right? So how and why are we able to do this Healthcare 5.0? So the main technology enablers are the concept of digital twins, edge AI, robotics, and multimodal AI. Multimodal AI is nothing but, say, an LLM. If you see ChatGPT, when it first released in, say, 2020, 2021, it was able to only accept text as an input. But now when you use ChatGPT, you're able to add image attachment. You're able to add a Google Doc. You're able to, you open the mic button. You're able to talk. You're able to submit a voice input, which it converts into text, and it's able to understand. That's multimodal AI, where you're able to use, especially large language models to have different signals, sound signal, visual signal, textual signal, everything, and use all these signals at the same time to make a prediction, right? Robotics, as we know, is robotic arms, etc. Edge AI is nothing but these small chips. So if, for example, we see Apple Vision Pro was very popular 2 years ago, so everybody was able to wear it and have the entire screen in front of their eyes. So Edge AI is able to enable such a big billion parameter model to be able to sit on such a small device, right? And Edge AI is very important also because you have to reduce latency. Okay, whether the inference is happening on the cloud or whether the inference is directly happening on the device, Edge AI enables us to determine all that. Digital twins is nothing but a simulation, right? We'll go into digital twins soon, right now. So I'm going to brush over this slide. Okay, personalized medicine with AI. So yeah, we'll go brush over this as well. Yeah. So digital twins. So now, digital twins. Imagine if every patient had a virtual twin living inside a computer, right? So this particular simulation will have the same heart, the same lungs, and the same medical history. But you can experiment as much as you want because it's just a simulation. This thing, right? So actually, digital twins were originally used in spacecraft explorations. So they had a digital twin of that particular spacecraft, and the scientists made sure that what would be the effect of pressure and stress on that spacecraft, and then later only they put the real humans inside it, right? So that is a digital twin is nothing but a computer generated replica of a real world object or system. What is the difference between any simulation and a digital twin? A digital twin is an actual object, right? And you're simulating the effects and impacts of something on that object, whereas a simulation is something which is basically before you deploy something or before you do something, you're going to see what the impacts are. So it's not a living version that is constantly being updated, but a digital twin will constantly be updated. Say, for example, I can treat a patient by giving him a medicine and then seeing what would the impact on his on his body be based on his genomic health, etc. Right? And if I see that this medicine is not working out, I'll immediately be able to change that different medicine. And how will I be able to do this? Because that digital twin has the entire medical health history, genomic data, etc. of that particular person in that simulation. Right? So sometimes it could be just one organ that we are trying to do, like in this case, okay? And sometimes, digital twins are used in healthcare to simulate an entire hospital environment, like, okay, where the departments should be, who should be on call, who should not be on call, and who's going to answer when what happens. So something like a production environment also in healthcare, digital twins help in assessing. Right? So treatment simulation, surgical planning, drug testing, and hospital operations. These are the main applications of digital twins, right? So the next main frontier behind this healthcare 5.0 is genomics and AI. Okay, so variant prediction and interpretation. So every person has so many genetic variants, but only some of them are linked to a disease, right? Traditionally, geneticists had to annotate these variants manually, which was very slow and error prone. So now deep learning models are able to classify these variants with 93% accuracy, and whole genome sequencing analysis can happen from weeks to hours. So over here, I'd like to tell about one particular project in my workplace. So this was for a company called Jazz Pharma, and over here we are not trying to do the genomics for variant of gene prediction, but it was mainly used for drug discovery. right? So basically, this pharmaceutical company, they had a lot of scientists and they wanted to find some stable compounds that they can experiment with and find these drugs, right? But it took them days and months to figure out some stable compounds by, just adding a oxygen molecule, removing a hydrogen molecule, something like that, right? So using deep learning, what we did was we generated so many molecules like this, right? And what we did was there was an external library with which we can validate which of these molecules can or cannot be stable. And these are all synthetic molecules which do not exist, right? So then after like shortlisting about 40 of these molecules, we give it back to the scientists, and the scientists are then able to use those 40 shortlisted molecules in their drug discovery process, and their drug discovery has become so much more faster. So what used to once take months and is now happening in weeks. And so this was a very successful project, and it's happening in the company that I work for right now, right? Then pharmacogenomics, right? The same drug can have very different outcomes in different patients, right? Well, one patient might improve, another patient might suffer some side effects, right? So say, for example, 2 cancer patients might get the same chemotherapy. One of them might cure it quickly, but the other might have toxicity. AI is able to predict this effect on the human and adjust the dose before the harm is done. Okay, and disease risk stratification, right? AI and polygenic scores combine thousands of small genetic markers. Okay, this predicts diseases decades before any symptom might show up. Okay, and some of the places where it's used is in predicting coronary heart disease, type 2 diabetes, and certain cancers, right? Say, for example, a 25-year-old might know that their genes and lifestyle is putting them at a high risk of diabetes by the time they turn 45, right? So right now itself, the AI can predict that and say that, okay, intervene this with diet, exercise, and you can prevent this from happening, right? And then personalized treatment pathways. So the clinical decisions that we get from AI, with that, we are able to combine multiple factors like your genomics, the imaging results that you get, your lab results, the history of diseases and the history of sensitivity that you have. And, you're able to go intervene and make decisions and prevent things from happening before they can even happen. So applied case studies. So have another notebook. I'll brush through this a bit more quickly. So over here, what I've tried to do is I'm trying to use computer vision, and I'm going to show how the structured data and supervised learning and unstructured data is able to do the prediction for a healthcare task, right? Over here, I'm taking a skin cancer data set, right? So I've just downloaded a Kaggle-based data set, right? And here are the kind of labels that we have. Okay, so in skin cancer, there are so many types like melanocytic nevi, melanoma, benign keratosis like lesions, basal cell carcinoma, actinic keratosis, vascular lesions, and dermatofibroma, right? So I don't have a lot of data here as well, in comparison to an average computer vision task. So over here, I have almost 40,000 samples in my training set and 2,000 samples in my validation set, right? So here I've visualized this data. So there are like 1 or 2 images for each type that we have, right? So here I have used a very lightweight model, which is called MobileNet V2. MobileNet V2 is also one of the most popular models used for edge AI kind of tasks because it's so small and it's lightweight, right? So here I'm just training the model with just 10 epochs, just for a demonstrative reason. And here I'm predicting, right? So here we can see the training and validation accuracy, training and validation loss. So the blue line is the training accuracy and the orange line is the validation accuracy. So training accuracy, we're able to observe that it keeps increasing with every epoch, which is actually a very good sign because accuracy keeps increasing. And with the validation loss, we can see that the loss is keeping on decreasing, right? So the training loss is keeping on decreasing. That's also a good sign. But we are able to see that the validation accuracy is more or less where it was. It's not increasing or decreasing. This is a classic case of overfitting where the model is performing very well on the training set. So I know that my model is learning, but if I give it a sample data set, will it be able to predict it correctly, it will not be. So this means that I have very few samples for the model, or it could be many other factors as well. But yeah, it could be that maybe I have to make a lighter model and stuff like that, and I'll be able to avoid overfitting over here. All right. So yeah, so basically convolutional neural networks, NLP and LLMs in healthcare, right? So healthcare, we have so much text, right? There's doctor's notes, patient conversations, then there are research papers, etc., right? So AI is going to help us to consolidate all that information. There are also so many rules around, okay, what does the IMA recommend? What does the FDA recommend? What does the WHO recommend? So doctors are able to use NLP and LLM to kind of guide them to do the proper diagnosis, right? And know, what would be the downfalls of using a system over the other, right? So yeah. So now this is something that I am doing in my workplace right now, which is basically the health insurance company, right? We get lots of insurance papers from so many different hospitals, and each hospital has its own format of how a form must be. Now, I need to make sure that all this information is centralized and digitized so that it can be used for many other downstream tasks, right? The fact that the format of every single hospital is different should not stop me from being able to effectively digitize and figure out which patient shall I offer the insurance to and which patient shall I not offer the insurance to. So I use Azure to perform optical character recognition. So that's like LLM, computer vision based model, to kind of understand these PDFs. Then I pass it through my custom GPT-4, which is a local GPT-4, and figure out like 40-50 key factors of what I want from this information, and then I push it into an SQL database so that it can be stored and used in downstream tasks. And also the information that I'm extracting from these patient records, like what patient has what disease and how many visits have they come to, all this. I've also made a chat bot that any person can ask, oh, in the last month how many patients came, and in the last month how many patients were diagnosed with this specific disease. Things like that are able to be more searchable right now through like a custom chatbot as well. So this is just a little tidbit about what I do at work. IoT and edge in healthcare. So as we spoke earlier, so basically the watches and the smart clothing that comes these days, and so many tracking devices, glucose monitoring devices, right? And so with all these kind of devices, when the doctor visits you, you don't need to explain, because one defect of traditional healthcare 2.0 or allopathy is your treatment is based on how well you're able to explain your situation. But now you have the data to back it up, and the doctors have actual data to look into, and whether or not you're good at explaining, they'll be able to give the right treatment for you. And this is enabled by edge devices, right? So large models have billions and millions of parameters. Edge devices need lightweight and efficient models. So the MobileNet V2 that we saw right now was one of the best examples for a good model to use on edge devices. And other than that, there are techniques like model compression, pruning the model, and quantizing the model. So basically, instead of making the prediction in 16-bit float, you need to train the model to make the prediction in 8-bit float. And that makes a huge difference into how quickly and the model is able to make these predictions, how much space it occupies on the small device that you're wearing in your hand, etc., etc. So the development of IoT has enabled all of this to happen right now, right? So here are some examples of robotics in healthcare. So some examples that are already existing is a Da Vinci surgical system, okay? And it's used in thousands of hospitals, right? So it has like the robotic manipulator arm, which is dexterous, okay? It has 3D vision to be able to do minimally invasive surgery. So say, for example, these keyhole surgeries, etc. So they benefit from this Da Vinci surgical system. And Google's Johnson & Johnson Verb Surgical, right? It develops digital surgery platforms where AI guides the decisions in real time. So this is already existing. AI-powered prosthetics, I will show later an example of one of Elon Musk's very own company, which is Neuralink. And what it is basically, we all know about Stephen Hawking and how he was able to sit in a wheelchair and be able to communicate despite not having the, physically not being able to do it otherwise without the help of his, smart chair. So Neuralink is a small chip that is inserted into the brain, and the person is able to control what they do with basically the cursor on a computer, right? It's almost like a Bluetooth connection from his brain to his computer. He's able to play chess. So we'll look into that video in just a bit, right? There are like prosthetic legs and there are arms. There are many companies that make these, and these are very much reality right now, right? And then service robots in hospitals, right? We might have seen this in restaurants as well. So there are robots that can accurately go and pick the surgical instruments. Okay, what kind of tongs are needed? What kind of scissors are needed? How many of these are needed? What kind of products are needed? Also, food to be delivered to the patient. So instead of nurses working overtime and doing everything on their own, these service robots are able to do it with much better precision, accuracy, and deliver the right products to the right places. So yes. So yeah. I think we already spoke about the IBM Watson. IBM Watson product, which is basically, it was for the case of oncology. I think I said it was for sepsis earlier, but basically it was trained on synthetic data, which did not translate to real-time predictions, right? And COVID-19 predictive models, most students do it in their final year projects, right? But can it really be used in real time? It cannot be, because it's not made for a production environment. The model is not robust, right? It's not able to, keep up with the mutations that can happen, and etc., etc. So these are some of the examples of how the predictive models or how an AI model can fail, right? So what are the current challenges? The data silos and interoperability. So basically, say Apollo Fortis has its own format of how it maintains the data. Fortis has something else. So it's not transferable. The data cannot be just moved around. Bias and fairness. So this was very interesting. So apparently the pulse oximeter, which like the doctors put to measure your blood oxygen level on your finger, apparently if you are darker skinned and you had hypoxemia, okay, which is basically, I think, lower blood oxygen level, it would miss you. Why? Because it was biased based on the skin color. So patients who had darker skin were always predicted with higher blood oxygen level than the patients with had a lighter skin. So these are some issues of bias and fairness. So you need to make sure that the data set you're training the model from is completely comprehensive. Regulation and ethics, right? So people don't know exactly how and what to use AI in, and how and what to not use AI in. So we know when and what to use IT software products in, but to what extent can AI make the decisions? What decisions is an AI allowed to make? So, and if you're not supposed to have bias and fairness in your particular model, but does that mean that you can take very private and sensitive data of a patient to be able to train your AI? Will that itself bias your model, or will that stand against the fact that, based on the HIPAA Act or other acts, a patient is supposed to have confidentiality over their diagnosis, over their conditions, etc., right? And if every patient wants the confidentialities, then how and where are you going to get the data from to train the AI? But these are all big conversations that still need to happen in this space, right? So these are some suggestive opportunities for the faculty, which is basically, collaborating with the industry as much as you can to be able to understand how you can equip the students for tomorrow's evaluation, right? Now I'm going to show gait robotics, right? So this is basically, a walking assistant. So for people with something like cerebral palsy or Parkinson's or anything. So how they're able to do the recovery and physiotherapy using an AI device. So we move on to the video. Can you all hear?
No. Can you play that again?
Okay.
Yeah. Yeah, past it,
Yeah,
yeah.
let me share with the video. Couldn't share sound. Okay. So are you able to see the screen?
Yeah.
And
Yes.
let me know. Okay, let me know if you can hear the video. Okay.
Lexo is a game-changing robotic therapy device for the lower
Sorry, is it audible?
Yes, audible, yeah.
Okay, yes.
extremities that offers a new standard in gait therapy. The device promotes therapy progress by boosting patients' net therapy time with its fast and easy setup. The active training mode facilitates specific gait element training, such as weight shifting and load bearing. The integrated Pelvis Plus system emphasizes Lexo's high adaptability to the patient's needs. Another of the device's standout features is its low overall height, making integration in existing and new facilities easy. Lexo offers different transfer options specifically catered to the severity of the patient's condition and their existing functionality. The lifter transfer enables the therapist to raise and position the patient effortlessly, whereas the self-transfer mode offers mildly impaired patients the possibility to slide into position independently. The intuitive setup allows the therapist to focus entirely on the patient and their personal rehabilitation goals. Furthermore, Lexo's Pelvis Plus guidance system can be adjusted seamlessly, which guarantees a physiologically correct posture and encourages a natural gait pattern. During therapy, step length and cadence can be set to optimize rehabilitation without interruption, which further increases net therapy time. Immediate biofeedback monitors the patient's own activity during different phases of walking and active weight transfer, which contributes to the continuous improvement of the main goals in gait therapy. Lexo's strength lies in the encouragement of the patient during gait rehabilitation. The task-oriented training requires active weight shifting, load bearing, and concentration on specific gait elements, such as the initial contact. This further promotes the patient's self-activity and a physiological walking pattern by providing only as much support as needed. The potential for a faster, more efficient rehabilitation increases. Lexo's virtual environment inspires the patient's will to succeed. Direct biofeedback also facilitates a high motivational drive. Tyro Motion aims to help patients in improving their independence and quality of life. Lexo helps patients to take the first steps to get better every day.
I know this.
So that was an example of robotic involvement in healthcare 5.0, and that's not the only machine that's there. There are so many prosthetic machines. There's so many bionic arms and exoskeletons, that are used these days, and it's really helping patients improve their quality of life. So this one is my most favorite of all the existing things, and especially there's a big hype around it since it's one of Elon Musk's passion projects, right? So now we're going to look into Neuralink.
In January, Elon Musk announced his company Neuralink had successfully implanted a chip in a human. That person is now sharing how his life has changed since. Will Reeve with the story.
I didn't have anything to wake up for in the morning. And this has changed that for me.
In a GMA broadcast exclusive, Nolan Darbaugh, the first human implanted with a Neuralink chip in his brain, is telling his story.
I accepted that I was paralyzed and that was my life. I always held out hope that it would all get better.
At 22 years old, Nolan says he dove headfirst in waist-deep water, struck something, and sustained a spinal cord injury. He couldn't move from the shoulders down.
From the time of your injury until earlier this year, what was your daily life like?
I mean, one thing about being paralyzed is that there's a lot of time to sit and think. So I thought through basically my whole life and realized all the mistakes I'd made and what I could do better.
Then, just last year, Nolan, now 30, receiving a life-changing opportunity.
One day, one of my buddies from college called me up. We talked pretty regularly, and he was like, hey, Neuralink, they opened up the human trials. And I said, what's Neuralink?
Neuralink, co-founded by Elon Musk, is an experimental implantable brain-computer interface, or BCI, a chip surgically implanted by a robot and connected by threads to a patient's brain that allows the patient to control a computer or smartphone with their mind.
This is all from there to there.
Yeah, man.
Wow.
Neuralink is not the only company working on this technology. Several others are also testing their BCIs in paralyzed volunteers. Noland now joins that small group as Neuralink's first patient.
I was just very happy that I would be a part of something that I believe is so monumental and this next step forward of helping people with paralysis.
What can you do now with the chip implanted that you could not do prior?
I can control a computer just like anyone else can, which is not something I was able to do beforehand.
You just played some music?
Yeah, man.
That's awesome. Do you worry because you are the first patient that something unforeseen could go wrong now that this is inside your head?
I wouldn't say worry. It was something where I knew that if I did this, then it would take a lot of headache and heartache away from the people down the road.
Just last week, news that some of the threads in Nolan's brain had retracted, affecting the performance of the device.
How'd you take the news when they told you?
So basically, in the interest of time, I'm going to cut that video short. But ultimately, the thing to note there was how he was able to just think about where he wanted to move his cursor, and he was able to control which song he was playing. And further down, there are videos where he plays chess, etc. And yeah, if like y'all are interested, you can definitely go and look it up on YouTube. And yeah, with that, I'd like to conclude today's session on Healthcare 5.0. I hope I did justice to the topic and I explained about predictive and personalized AI, the techniques that are there. And I'd like to really thank Mani Bharti sir for remembering me for this session and for giving me this opportunity. And he was my ex-professor, and he always, motivated me and made me trust in my abilities. So I'm really happy to be able to give back to the community right now. Thank you so much.
Yeah. Thank you, Karthiga. Really great to see you presenting so nice and so wonderful session, right? You covered from the scratch and you see what is happening in the industry. Yes, sir. What I can say within the time constraint, you have shown the good videos, right? It's really good. Just I want to add a point. I want to see that part 6 slide you have shown the faculty or what they can interact with the industry. Can I share that again?
Mm-hmm.
Yeah.
Oh yeah, of course. Yes, I can.
It should be useful for the researchers to take up.
I'm also happy to share the entire slide deck and and the notebooks, everything as well.
Okay,
so
great.
Just give me a moment. So
Yes.
yeah. So basically, just as with any other kind of engineering domain, right? I think the most important thing for the role of faculty is to be able to collaborate with industry leaders in that particular domain, right? Say, for example, people from, say, Johnson and Johnson, or Toyota also is a big player in gate robotics, right? So companies like this, which have a presence in India, if you're able to collaborate with the leaders, the pioneers over there, and be able to incorporate some of those techniques into the syllabus, right? Either like one-day workshops or something like Edge AI. And most of these concepts like twin digital twins or Edge AI, IoT, these are not only specific to Healthcare 5.0, but rather it's currently what's happening all across the industry in all the domains as well, right? So as I said, digital twins was originally there for space exploration, right? And digital twins are also there for, say, for example, wind turbines, windmill monitoring, and any kind of machineries are there. So you use digital twins to do those simulations. So concepts like that, if they are incorporated into the syllabus, right, then I'm very sure that that will really benefit the students, especially in this core domain, getting into robotics. Even Robert Bosch, for that matter, also is a big leader in the prosthetics, limbs, and all that. So that's my main kind of observation and suggestion from this slide.
I have one more query. You explain about that MobileNet V2 for the skin disease prediction, right? So it's a lightweight model. Yeah. So can it be?
That's right.
Can it be taken? The model can be brought into a Raspberry Pi and made it like a standalone device. Is it possible?
Yes, it can be. So that is the main kind of application of the MobileNet V2. So if you see something like ResNet 50 and all those other models that came before that, InceptionNet, they were very, very huge and they could not be taken into a model, right? But MobileNet is something that can be put onto like a Raspberry Pi or any other small models as well. Yes, so definitely that is a possibility.
Okay. And I can unmute the participants, right? Those who are interested can... participant can unmute themselves and ask a query, or else they can ask the query in the chat box. We can wait for a couple of minutes, Karthiga.
Yeah, sure, no problem at all.
Yeah.
Yes.
Any queries you can ask in the chat box. Yes, someone is asking a question. Edge AI. You can see the chat.
Edge AI power is a concern. How to overcome complex calculation? So Edge AI power is a concern. So basically, my source, how I know how and when to use Edge AI is basically Google has very good resource material on its page. Right, and TensorFlow Lite, basically it's able to convert any ONNX formatted deep learning model and figure out how to deploy it and how you can track the metrics, how to reduce the power if power is your concern, how to reduce the latency if latency is your concern, right? Which it even gives you a split as to which of the deep learning layers are the ones that are contributing to that excess latency or excess power or excess time, whatever it is that you are optimizing for. So I'd encourage to kind of like take advantage of the TensorFlow Lite documentation from Google. Yeah.
Great. Thank you.
Yes.
Okay, Karthiga. Thank you very much. Yeah,
thank you, everybody. Thanks a lot.
Really wonderful.
Yes, very nice seeing you. Thank you. And also, congratulations to the committee for bringing this initiative for the first time. And I really hope that this happens every year. And this is a good way to have the industry faculty, coordination as well. So I really hope that this is successful. Thank you. Good luck to you all.
Yeah. Thank you. Thank you, Karthiga. Bye.
Yes.